right, we're getting more practice review of exponents and logarithms. So remember that when it is spelled log, it is a common log because the default base is 10. So here we are saying what exponent should we put on 10 to get a result of 1. So our logarithm would be 0. When it is spelled ln, then of course we know the default base is an e, so we're not always going to write that. When it's a natural logarithm, the base is the natural base e. It's as simple here as saying we would like to know what logarithm or what exponent should we put on e if we want a result of e. Well, I guess that would be an exponent of 1. So there's your identity property. The natural log of e you will always replace with 1. In question 3, we don't have a default base. We are told that our base here is 2. So we're saying what exponent do we put on 2 if we want our result to be 32? And always look to see it's not a calculator problem. If it is a perfect power, then you know the logarithm. So you don't always need calculators for logarithms. Like question 4, where the base is 8 and we want to get a result of 1/2. So hopefully you would say, well, I know that the cube root of 8 is 2, so a cube root as an exponent is the 1/3 power. So if we put a 1/3 exponent on our base, that would give us a 2, and then we would simply need to do its reciprocal. So we want to do a negative 1/3. So remember that in an exponent, the numerator is a power, the denominator is a root, and the negative is a reciprocal. So remember that negative exponents have nothing to do with negative numbers. Negative exponents create reciprocals. In number 5, we're doing a common logarithm. So the base is 10. So how do we turn this into 1/1,000th? Remember, count your decimal places: tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths. So every decimal place. So the question that many students will have is, should this be a -6 or a -5? Perhaps one thing that might help you out here is think about 1/10. The very first decimal place, if you write this, you know, is already a -1 exponent. So you count each of those decimal places. So 10 to the -6th is 1/1,000,000th. In question 6, this time our base is the fraction, and we want the logarithm that produces a result of 8. So 4 and 8 are both base 2 numbers. So you could show a little bit more algebra, but I suspect that you guys might think of it step by step. Here's what I would do. I would say, well, a negative exponent is going to turn this into a 4. And then if I did it square root, that would turn it into a 2. And then I would cube it to turn it into an 8. So stop and think about it again. If you start with 1/4, the negative is the reciprocal 4. The denominator of 2 means square root, which would be +2, and then raise it to the 3rd power. Here's your algebra method if you prefer. So we could write 1/4 raised to the x power is equal to 8, and then we could rewrite this. 1/4 we know is 2 to the -2, and 8 is 2 to the 3rd power. So we know that power of a power, remember you multiplied exponents. So we know that if the bases are equal, then our exponents must be equal, and then you could solve it using this algebraic method. But I think the idea of breaking it down to a common base, you guys should be able to do that by inspection. So a little bit of practice and you'll remember your logarithms, I hope. All right, 7, we're back to a natural log. So we want to come up with 1/e to the 3rd. So another way, lots of different ways of thinking about this. I could say that this is e to the -1, so I could rewrite it this way. And then you could say, well, what base do I put on e to turn it into e to the negative 3? I think you can see just by observation that's negative 3. But one other way students might say is, remember that our property of logarithms is that the log of a power, we can bring the power down in front. So negative 3 times, and here's our identity property. We know that the natural log of e is 1. So there's more than one way to think of that problem. In number 8, here's an inverse property. E raised to what power would produce the natural log of 5? Well, these are inverse operations. So we would have a 5 there. And in number 9, please don't put natural log squared here. Order of operations, we have to work inside the parentheses. The natural log of e to the 5e power. The natural log of e to the 5e power. Well, again, if you start getting confused here, you can say the log of a power is the power times the log. So inside those parentheses, we could bring that 5e in front if you wanted to. And then we know that this value is, of course, 1. So now we have the natural log of 5 times e left over. The natural log of 5e. Can we do anything with that? Let me scroll over to get some space to write here. I'm just going to erase some of this previous problem. So what could we do with the natural log of 5e? Remember that the log of a product is the sum of two logs. So one thing that you might do here, the log of a product becomes the sum of the logs, and the only reason we might do that is because we see an identity property built in here. So instead of leaving it as the natural log of 5e, perhaps a better answer might be 1 plus the natural log of 5. That's an exact answer, by the way. So you could use your calculator to approximate it to 3 decimal places. But remember that we're happy with exact answers. All right, again, no calculator. Otherwise, we could use calculators to solve some of these. And notice that in problem 10, both of these bases are base 2 numbers. So I can think of this 16 as 2 to the 4th. And now we know that power of a power property, exponent on an exponent, we multiply these exponents together. So we have 2 to the 4x minus 12 is equal to 2 to the x. The only way this equation could be true if the bases are equal would be if the exponents are equal. So we'll have 3x is equal to 12, and of course x would be equal to 4. You can go back to your original and check it out here. If we did back substitute, put a 4 in there, we'd have 16 to the 1st is equal to 2 to the 4th. So, as always, check that your answers are reasonable by back substitution. We have something very different in number 11. Our bases 7 and 5, clearly those are not equal bases. So to solve this equation, but it says no calculator here, what can we do to get a variable out of an exponent? To get a variable out of an exponent, we rewrite it in logarithmic form. So you could use this as a log base 7, but I'm going to ask you to take the natural log of both sides. Take the natural log of both sides. So it would now look like the natural log of 7 to the 2x plus 1 is equal to the natural log of 5. And the trick of taking the logarithm of both sides is because now we have the log of a power, and the power comes down in front of the log. So the only way to get a variable out of an exponent, if it's not a perfect power, is to use logarithms. So the inverse of exponentiation is to take logs of both sides. So now we have 2x plus 1 times the natural log of 7. And remember, the natural log of 7 is just some number. So now I'm going to solve for x. I'm going to divide both sides by that natural log of 7. Then I'm going to subtract 1 from both sides. And then I have to divide by 2. So however you want to write that. So we might, if I come over here where I've got some space, I might multiply both terms by 1/2, for example. So I might put a 2 in each of the denominators. So, or you now have a common, you could get a common denominator and put them together, but I don't know that that's necessary. So I think I might write it this way. I could notice that there's no variables here. This is a number. So you could, if it had not said no calculator here, you could have used your calculator and rounded your answer to 3 decimal places or more. All right, we need to solve for x, and this time our x is trapped inside a logarithm. So I'm going to need to use exponentiation of some sort because that's the inverse of logarithms. First, I'm going to see if I can simplify this. The difference of 2 logs comes from the log of a quotient. So you can see how that would really simplify this problem. So now we have the natural log of 2x is equal to 7. And now we know that the base here is e, so we can use our definition of a logarithm. This is equivalent to saying e to the 7th power is equal to 2 times x. So x would be 1/2 of e to the 7th. And 1/2 of e to the 7th is a constant. And that is actually easier for us to write than rounding it off to decimal form. In 11, the sum of 2 logs comes from the log of a product, so I might want to put this back into a single log. The sum of 2 logs comes from the log of a product, so I simply multiplied x times this binomial. And now I can rewrite it as e to the 1st power is equal to x squared minus x. And now how do I solve this equation? Well, I set a quadratic to 0. So now remember that e is a constant. If I could factor it, that would be my choice. I don't know how to factor it, so I would go to quadratic formula. So let's see what we would come up with for our 2 solutions. So remember a, b, c here. So our quadratic formula, the opposite of b is 1, plus or minus square root of b squared minus 4 times a times c, all divided by 2 times a. So I have x is equal to 1 plus or minus the square root of 1 plus 4e all over 2. And there's an exact answer. Let's just transfer those 2 answers back here. And of course, I don't mind if you leave that as 1 fraction, or you might split that. Remember, if it has imaginary roots, then you were to split it into a plus bi form. But these are all positives, so you have real number there. The problem in 14, we only have 1 variable, so perhaps let's move this 6 to the other side. How do I get a variable out of an exponent? I change it to logarithmic form. I can take the natural log of both sides. If there's more than 1 variable, that would be the method I would use. Here we know just by definition that the logarithm of 6 is our exponent, 2x plus 4. And solve this for x. So the natural log of 6 minus 4, notice there's no parentheses there, is equal to 2x, and divide by 2. So we could write, you could put 1/2 in front here if you wanted to instead of a fraction. Take 1/2 of each term though. So we would get x is equal to 1/2 the natural log of 6 minus 2. Find an inverse for the function. So remember, what you need to do for an inverse is you need to solve it backwards. So, and then change the variables. Some of you maybe in your algebra class changed the x and y right away. I don't know, for no reason that I know of. I always solve it for x first and then I swap the variables. So whichever order we need to solve it backwards and swap the x and the y. By definition, I know my base is e here, and this is the result we want to produce. So we know, this is the result we want to produce. So we know that e to the y power produces 5x plus 3. So we'd have e to the y minus 3 is 5x. I'm just going to reverse my equation now so it's starting to look like function form. Just going to swap the two sides here using symmetric property. And now I want to take 1/5 of each side. So I'm going to write it as 1/5 of e to the y minus 3/5. And then I can swap the x and the y, which you maybe had done earlier. Doesn't matter whether you change the variables first or later. And now I can rewrite this, but don't call it f of x. Remember, your notation for inverse is to put a -1 symbol on the f. So that is not a reciprocal. That is a symbol for the inverse of function f. So we could write it, and you could put it with e to the x minus 3 all divided by 5. That would be the same. Let me write it that way here so you can see that it doesn't matter either one of these two formats. But remember to change the y into f inverse of x. But I don't care whether it's in binomial or monomial form. And let's look at some graphs. We know that e is approximately 2.7. I hope you won't forget that. And a positive number to the 0 power will produce 1. There's our key point for an exponential graph. When x is 1, we'll be at about 2.7. When x is -1, we'll be at 1 over 2.7, and it'll keep getting smaller on the negative side. So this is key point here, no matter what the base is. And remember that I've asked you, whenever you have an asymptote, to put its equation. Y equals 0 is a horizontal asymptote. So in 17, we've got some transformations of that graph. So some order of operations. First, this negative on the x means that when I used to pick +1 for x, now I would have to pick -1. So this is going to be a horizontal reflection. Negative x's will do what positive x's used to do. So that horizontal flip or reflection makes the graph look like this. And then we're doing the opposite on the outside of that. So there's our vertical reflection. So now I could take that graph and flip it. And then this one is a vertical shift. This is a vertical translation, so it's going to go up 1 unit. Vertical shift up 1 unit. So I'm going to take this, which had its y equals 0 asymptote, so the asymptote is also going to move up. So the entire graph, so the key point originally, sorry, I'm not doing very nicely marked graphs here. The key point originally was at 0, 1. Then it flipped down to 0, -1. And then our key point slides up 1 unit. So our key point for our final graph would be at the origin, and our asymptote would be at y equals 1. So the graph keeps going this way, but it gets very close. The right-hand behavior, as x approaches infinity, the right hand of the graph approaches the asymptote. All right. And a logarithmic graph is the inverse of exponential, but I hope you can think about natural logs. Pick the easiest values you can for x, and I hope you're still not making xy charts, but the easiest things you could pick, of course, for your x's are powers of e. So you want to pick, I want that to be a 1, e squared. So you want to pick values that have easy natural logarithms. So I hope you're not still making these xy charts, but I hope these points are in your head. This key point, the logarithm of 1 in any base. Remember, our bases are always positive bases, by the way. So a positive number to the 0 power will always be 1. So logarithmic graphs, as their key point, have 1, 0. And we know that 1 over e squared is something like 1/7. So at 1/7, we're down at -2. So we can tell that we'd have to go over to e to get an exponent of 1 and over to e squared to get up to 2. So we know that these graphs are slow risers. And we know that we now have a vertical asymptote at x equals 0. So if you mark the key point for me and the asymptote, that would be enough. Now we're doing a transformation. So here the +2 is changing our x value. It's inside the function. So where we picked 1 before, now I would want to slide that over 2 units to the left. So I want to compensate by going left 2 units. So our vertical asymptote used to be at 0. So now our vertical asymptote is now at x equals -2. Our key point that was at 1, 0 slides over 2 units. So it is now at -1, 0. But we have a rigid transformation. This is still the same graph. Just move 2 units to the left. Oh, I'm sorry. I missed this negative sign. Let me, that would be a dotted graph. Nothing wrong with what I did. I just didn't finish. There's one more change here. This is a vertical reflection. Changes the y coordinates. So all the y's that used to be positive are now negative. All the y's that used to be negative are now positive. So this is our final graph. But it still has this same key point at -1, 0. Feel free to make those dotted step-by-step graphs if you wish. All right, let's see if we can finish quickly here. Give the domain of this function. Well, what numbers can you take logarithms of? So think about your basic graph. We can only take logarithms, so our domain of this graph is everything from 0 to infinity. We can't do a natural log of a negative number. E is our base, so is there any exponent we could put on e to get a negative value? So here our domain, x plus 3 has to be greater than 0, so x has to be greater than -3. So in interval notation, as our directions ask for, we would have -3 to infinity. So this is our horizontal shift left, and then we're going to do this vertical flip here, vertical reflection. And then this is going to take everything up 2 units. So if we think what the graph is going to do, think of our basic logarithmic graph. I'm not going to do this very carefully. I'm going to go 3 units to the left. So there's our asymptote now at -3. The vertical flip, the graph used to look like this, so the vertical flip goes like this. And then adding 2 units to it takes our key point from -2, 0 up to -2, +2. But our graph still is eventually going to cross the axes and go forever here. So this is basically the shape of our graph. So the range of the graph here should be all real numbers. And with transformations of e to the x, so again, always have your basic graph in mind. Here was our key point at 0, 1. So this is our graph of y equals e to the x. So now we've got a shift left 1 unit and then down 2 units. So if you actually want to make a quick sketch of the graph, that might be quickest. So our key point is going left 1 unit and then down 2 units. So our asymptote used to be at x equals 0. So it is going down 2 units also. So we have no flips here. We're just going 1 to the left and 2 down. So our graph now has its key point at -1, +1, I believe. So our domain is all real numbers. The x's can be anything we want, but our range goes from -2 to infinity. And make sure with a horizontal asymptote that you have an open bracket there. It's everything above -2.